So we've talked about this general solution for lateral trim, and remember we're using small angle approximations for beta, delta A, delta R, and I left in the sign of phi here, but you could also drop the sign and make this a small angle approximation where it's just the weight coefficient times phi. So these are our three equations. They have to all sum to 0 in order for the aircraft to be trim laterally. And so, and one thing that we learned through this is that we actually have four, I'm going to call them unknowns. So beta, delta A, delta R, and phi that can be used to trim this aircraft. Now, the pilot only has control over delta A and delta R, but what he chooses for those will produce a different solution for beta and phi. And there's actually an infinite number of solutions here that he could choose. So let's look at why we might choose one solution over another. And one of the most common cases is what's called the steady heading side slip. So steady heading side slip is a time when beta is going to be specified, and we're going to need to solve for delta A, delta R, and phi to solve these equations. So when would be a flight scenario when beta is specified, when we really don't have any choice about beta? Well, that's going to happen when we need to keep our heading. We want to have a steady heading, so we don't want to change our heading, and there may be some cross flow or crosswind to that heading, and so that's creating some side slip. So let's look at one of the most common cases for this is actually just takeoff and landing. So let's draw our runway here. So here's our runway. That runway is mounted to the ground. We can't change the heading of that runway. We've got to take off and land in line with this runway here. Well, it's very common, it's not uncommon, to have some crosswind, some atmospheric wind that is not aligned with that runway when we're taking off and landing. So this is what's called the crosswind landing. And so the pilot has a couple choices they can make. If they want to keep their aircraft, and I'll just draw a simplified airplane here. So let's say that they want to keep their aircraft nose aligned with that runway. If there's some side slip here, now remember that because of this, there's some non-zero beta. Well, if that's the case, then they are also going to have to bank the aircraft, okay? And so I'll just draw from the back of this aircraft. So he's going to have to bank the aircraft phi and have some non-zero bank angle in order to keep the aircraft oriented and moving in this direction here. Well, that becomes a little problematic because the wingspan of aircraft is usually rather large, and so just a very small bank angle will cause a tip strike during landing. So although this is an option for trimming the aircraft out so that he can keep the aircraft aligned with the runway, this is not very conducive to takeoff and landing because of a tip strike scenario here. Okay, now this of course would depend on the type of aircraft you're flying. An airliner has very large wings, or large wingspan. If you're flying a fighter aircraft, then you actually can have some bank angle here that's not too detrimental. Usually because those main wings are a bit stubbier, and you still sit a distance off the runway, depending on how the landing gear is designed. So but this is one option. Now another option is what's called crabbing the aircraft, and in this case, what they do is they actually point the nose of the aircraft into the wind, so they'll rotate it there. And so the aircraft will still continue to move in this direction, but they minimize the beta that the aircraft experiences. So this is called crabbing the aircraft, and so it's crabbed into this crosswind. And what happens is we've basically gotten rid of beta, but we've changed the orientation of the aircraft relative to its heading. So it's still moving in this direction, but it's oriented with its nose pointed into the wind here. And so what that does is it gets you can make beta really small and therefore phi really small and trim the aircraft with a nearly zero bank angle. Theoretically, you can get to a zero bank angle. Now, this is challenging, though, to land because now when we touch down on the runway, our landing gear is not aligned with the direction of the runway. And so what you'll see quite often is that the aircraft will do this as they're coming in on approach, and so they're crabbed into the wind, and just before they touch down, they'll kick the rudder over, and so it'll swing the nose of the aircraft over to be aligned with the runway just as they touch down. And so I'll drop a link to some crosswind videos down in the description here, and you can check out. There's a lot of videos on YouTube of crosswind landings. They're really fun to watch. Some of the bigger airliners are really interesting to watch, especially like the larger Airbus airliners. Anyway, it's just really fascinating. And some airports, some airports are notorious for challenging crosswind landings simply because they didn't have a lot of room to build the airport. So this is common in like larger cities like Hong Kong and Tokyo, places like that maybe they didn't have a lot of room, and so they had to place runways in locations that are not necessarily aligned with the dominant winds of the area. So a lot of times what they try to do when they design an airport is they try to align these runways with dominant winds, or they build actually a few runways. You'll see patterns like this where they have one runway here, and then they'll have runways oriented at angles, so that they can choose a runway that's located or that's oriented with the current winds, and then they can switch which runways they're using and what direction they're taking off and landing in order to minimize this effect. But as I said before, some airports don't have as much leeway, and so you'll get kind of some dominant side slip velocity. So anyway, interesting videos. You can spend some time on YouTube watching those. They're kind of fun to see how pilots handle it. And it's not uncommon for a pilot to have to abort the landing. And you'll see that as well, where they just don't feel like they have control of the aircraft as it's coming in, and so they have to do a go around and come in for another pass. So anyway, this is called the steady heading side slip. So let's look at the mathematics behind this. So in this case, we've got a velocity that it's just above our stall velocity, some velocity that we're trying to land at, right? And then we've got some crosswind velocity here. And so what we don't have control over here is beta. There's going to be some beta, or we have very little control over that. Now we can crab in, like I said before, but in this case, we're going to treat beta as a known value. And so we're going to rearrange these equations a little bit. First of all, we're going to actually neglect this term here. We'll come back and talk about this in just a minute. And why that's not so detrimental here. But we're going to say that goes to 0. And then we're going to say that beta is a known. So I'm going to take this column and actually move it over to the right-hand side along with beta. And then I'm going to take this column here and insert it into this matrix. Okay, so what we get now, if I just rearrange these equations, I'll have cy delta A, cy delta r, and cosine, the weight coefficient there, then CL delta A, CL delta R, 0, and CN delta A, CN delta R, and 0. Okay, so, and then our, we've got delta A, delta R, and I'm just going to put in phi here. You could carry around the sign of phi if you like, but I'm just going to put in phi and use a small angle approximation. And so that's equal to negative. I moved then that column over to the right-hand side. This is cy comma beta, cl comma beta, and cn comma beta, all times beta. Okay, so at this point we can solve for delta A, delta R, and phi to trim this out. So delta A, delta R, and phi are equal to the inverse of this matrix here, if we just brought that down. And remember, our minus out front from right over here, and then we're going to multiply that by the cy comma beta, cl comma beta, and cn comma beta beta. Okay, so we can we know everything inside of this matrix. We know this vector here. We can multiply those together. First invert the matrix, multiply it together, take the negative of that, and we can write this as the change in delta A with respect to a change in beta, a change in delta R with respect to beta, and a change in phi with respect to beta, all times beta, right? Because I'm just going to get three scalars in there. Once I multiply this through, I just end up with a vector, and the top scalar is basically, it's my proportionality constant between beta and delta A. The second scalar is a proportionality constant between beta and delta R, and the third is between beta and phi. So basically, once I've computed these, and this is going to be some value based off of the values in these two matrices here, once I've computed that, then I can just, from the small angle approximation, I can just plug in beta here, multiply it by this ratio or this value, and it will tell me exactly how much delta A I'm going to need. And this is linearly proportional because we're using these small angle approximations. Everything here is linearly proportional. So if I double beta, my aileron, my rudder, and my phi are all going to double for the values that they need to trim out the aircraft. Okay, so we can actually work through, I'm not going to work through this here, I'll just give you the solution, but you can actually invert this matrix, invert it and multiply it by that analytically. And so let me just show you what those solutions turn out to be. So we'd have a d delta A d beta is going to be equal to CL comma delta R CN beta minus CL beta Cn delta R over Cl delta A Cn delta R minus Cl delta R Cn delta A. The change in delta R with respect to beta is going to come out to be Cl comma beta Cn delta A minus Cl delta A Cn comma beta divided by Cl delta A Cn delta R minus Cl delta R Cn delta A. And then the change in phi with respect to beta comes out to be the negative of cy comma delta A times, I'm going to call it delta A comma beta. That's what this is here. Delta A comma beta, that's the change in delta A with respect to beta, plus cy comma delta R times delta R comma beta. That's what I'm going to call this guy here. Delta R comma beta plus cy comma beta. Okay, and that whole thing divided by the weight coefficient. Okay, so so these are our steady heading side slip gradients. That's what it's called, and that's what these terms are here. We've just analytically, written out what they're going to be once we fill out the values inside of this matrix and vector. But anyway, so these are our steady heading side slip gradients, and they can tell us some interesting things. So, for example, so once we plug in these values and we get some number for this change in aileron with respect to beta, change in rudder with respect to beta, and change in phi with respect to beta, let's say that that this term comes out to be 1.5, for example. So what that means is I'm going to take my side slip angle beta, going to multiply it by 1.5, and that's how many degrees of deflection. If beta was in degrees, then that gives me degrees of deflection that I'm going to need on the aileron to trim out the aircraft. And same with the rudder. Let's say that this came out to be 1. So for every degree of beta that I have, that means I'm going to have to add a degree of rudder deflection to trim that out. And then the phi, again, the same thing. We're going to multiply that to figure out what the bank angle is going to be. So these three are three angles that are linearly proportional to this angle beta that we're our side slip angle. So one thing that this can tell us is, for example, if this were 1.5 and this were 1, then that would tell us that probably our aileron is going to saturate before the rudder, if both of those had the same amount of degrees throw that they could deflect. So, if they could both deflect 30 degrees and it's going to take 1.5 degrees for every degree of beta to trim out the aileron compared to only 1 degree per degree of beta to trim out the rudder, then that means we're probably going to saturate our aileron before the rudder. So we're going to be limited in the side slip angle that we can handle because of our aileron design. So this helps us understand what's going to saturate first and what we might need to change on the aircraft in order to give us larger side slip angles that we can trim to. Okay, before we wrap it up here, I'd like to go back up here and just point out this assumption that we made where we dropped this term. It turns out that what we've done here can actually be used even if you have some asymmetric component from propulsion, as long as these delta A and delta R values and beta are measured relative to a trim condition with the asymmetric propulsion. So if we're talking about changes in aileron deflection and changes in rudder deflection, or changes in side slip angle relative to some trim state, you can still use the same type of process and use these side slip gradients.